Okay, well, let's get started. So we'll briefly talk about project number 2. We will continue in discriminant analysis today, and then we'll also start talking about project number 3. Are there any questions before we begin? Okay. So overall, the grades are good for project number 2. Just some very small things I wanted to bring up. Make sure you're using the correct notation. So I do expect you to fully use the equation editor. Your equations and stuff, your symbols should be exactly what's in the notes. So for example, don't type out, let's say, F1 hat like that. Don't type that out to represent like a common factor score. Rather, instead, actually use the equation editor. I'm not going to open it up right here, but actually put the hat in the right spot. Use an actual subscript, use the correct notation. Eventually at some point, pretty much all of you are going to have to write a thesis or a dissertation, and your advisor is not going to like not having the correct symbols to be used in the text. In fact, if you were ever to submit a paper to a journal, you got to use the correct notation. Make sure also that your code runs. Basically, what I see students sometimes running into is that, let's say you create an object in a separate program that's outside, obviously, the Word document, and you create an object, and then a number of lines later, you use the results from that object. Then when you copy and paste code and output from R into Word, you forget that object that you created earlier. And then if that happens, then I can't run your code. So just be careful about that. Also, there was a number of groups that when you were using complete linkage for the cluster analysis problem, your labels were saying that you were using nearest neighbor. Now, why did that happen? Well, you were copying and pasting code from my corresponding program. Just be careful, understand, okay, well, now that I'm using something different from how cluster analysis was introduced in class, I do need to make the corresponding changes in terms of the labels and object names. So, very small things. Are there any questions about the project? Okay, let's move on to continue with discriminant analysis. The basic idea here is that what we're trying to do is predict the group, or you could say also the population, from which an observation came from, using a set of independent variables. And the key here is that we know in our sample what group each observation came from. So it's kind of like regular old regression analysis, but instead of having a continuous variable as our response variable, now we have a categorical variable as our response variable. And to do this thing called discriminant analysis, basically all we need is this. We need to estimate the mean vector for group 1, for group 2, and eventually we'll get to more groups, group 3, 4, and 5. We just need to estimate that. So take the sample means for each variable for that particular group. Also, we need to estimate then the corresponding covariance matrix. For now, we're assuming that our covariance matrices are equal across the different groups. And so we have this what's called a pooled estimate to make this estimation. Later today, we'll look at what happens if they are not equal. And we just make a small adjustment. And there's a number of different, let's say, ways that we can take this information from this estimation to decide, well, what group a particular observation should be classified or predicted to be in. And one way is to use what's called Mahalanobis distance, which is very similar to a Euclidean distance. The main difference from what we did like with cluster analysis here, instead of having two observations looking at how far apart they are, instead we look at our observation and look at how close is it essentially to the center of that group I. But we also take into account the fact that there's different amount of variability in the variables, there's associations amongst the variables, so we put this inverse of the covariance matrix in there. And so for each group, for our particular observation, we calculate this distance. The group from which X has the smallest distance is what we classify or predict as the group for that particular observation. So we just look for the smallest distance. It's very intuitive. We can also rescale everything so that we can find what are called posterior probabilities. So the estimated, let's say, posterior probability of observation X being in group I is what's shown there. This gives us simply a number between 0 and 1. And so we look at these posterior probabilities, and the posterior probability that is the largest corresponds to the group that we predict that X belongs to. Okay. So R has a couple functions that we're going to be using to do this stuff. Just to review, the one that we primarily looked at last time was one called LDA. This stands for linear discriminant analysis. And the formula argument is where you specify your group variable and then also your independent variables. The formula argument is very similar to what you would see, like, for example, with the LM function. We can specify CV equal false. What that corresponds to is that we looked at a number of different ways that you can measure the accuracy of a discriminant analysis method or rule. And if I say false here, I'm going to be using a particular method called resubstitution. It's not the best method out there, but it's a nice method from which to start from. And we'll look at that more shortly. And then we also have an argument called prior. For now, we're going to assume, we're just simply going to say I have two groups, and each prior is going to be 0.5 and 0.5. We'll talk more about priors later today. And so, eventually what we get here is the summary of what's inside of the return result. And notice I called the return result DA1. The summary that we get is not too helpful. What's helpful is some stuff that's actually saved inside of DA1, such as the posterior probabilities. So we looked at last time, observation 1 had a posterior probability of 0.11 for group 0, 0.89 for group 1, so that 0.89 is greater than 0.11, so we classify or we predict observation 1 being group 1. And also just remember we're using the place kicking data here. So 1 corresponds to a successful place kick, 0 is a failed place kick. Okay. And let's see here. So I think that sets us up for, in terms of reviewing the material. Okay. So what I would like to do next is actually show that we can do some of the calculations, you could say, ourselves without necessarily relying on LDA. That function. This just helps reinforce that indeed that you know what's going on. You can do more than simply run one function. Okay. So what I would like to be able to do is essentially apply the Mahalanobis distance formula that we see there, and also the posterior probabilities formula there. R essentially gives us the posterior probabilities, but let's see if we can calculate it ourselves using the matrix algebra. Okay, so the first thing that I'm going to do, let me find where I'm at in my program, is in my place kicking data set, here's my first observation. Okay, so this is observation 1. This is going to be our X for now. And notice that the grouping variable called good is in there. And so I need to take that out so I have the data without that particular value. I just want to have, you can say, the independent variables themselves. And this is what now this is my X essentially. But I need to tell R, hey, this is not a data frame that I want to work with. Instead, I want to do some matrix algebra with it. So you can see the class that is data frame. So what I can do is I can tell R, hey, treat this as a matrix. Okay. And if I did class with that, you would see it is actually called a matrix. And if I take the transpose of it, now we have a column vector. So that column vector is what I'm going to simply put into X right here. Okay. Also, what I'm going to do is as follows. I need to calculate the mean vector for both groups. I need to find the estimated covariance matrix for both groups and then combine those two estimated covariance matrices together to find this overall pooled estimate. So how do I do that then? Well, what I can do is this. If I were to just take place kick $good equals 0, does anyone remember what that kind of code will actually return? Trues and falses corresponding to each observation in the data set. A true if it's equal to 0, meaning the failed population. 1 if one will be, it will be equal to a true if it's the failed population. It will be equal to false if it's the success population. And so when I combine this then with place kick here again, these trues and falses are in the row indice, and it will only return those rows that correspond to a true. And since I don't want the good variable, I want to remove the 9th column, and that's going to go into pop 0. And we can, and well, if I didn't remove that -9 there, let's actually just shortly do that. We can see that indeed I got all the good equals 0s. I don't want that good variable in there, so I'm going to put a -9 to remove that column from consideration. I'm going to do the same thing for population 1 for all the successes as well. I'm going to find then the number of good equals 0s, the number of good equal 1s by saying n row, the number of rows in that corresponding data frame. So we can see this is what we have. Notice we have many, many more failures than what we have for successes. That's going to play a role for us here that we will talk about later on. To find then the estimated covariance matrix for both groups, I use the co function as what we've done before. I put that into sigma.hat0, sigma.hat.1. So for example, here's sigma.hat1. Here's my estimated covariance matrix. Then to find the pooled estimate, again, what I want to do is use this particular formula right here. So notice what it is. I'm going to take my covariance matrix for, let's say, population 0, weight it by the sample size, take the estimated covariance matrix for the good equal 1 population, weight it by the sample size, and divide that all by another weight that looks at the number of total observations. And this is what I get. So this will play now my role of sigma hat then in my corresponding expression for that Mahalanobis distance. Next, what I'm going to do is find the mean for each column that's in population 0. So the average week is 9.89 for all the failures. I need to tell R, hey, I want to do some matrix algebra with it eventually later. So I say, hey, treat this as a matrix. I put that into an object called mu.hat0. So the mean value for group 0. Do the same thing for group 1. And there we go. So now I've essentially done all the math that I need to find every component of this. So now I can find each of those distances. So what I do then is simply put in that expression in terms of R's syntax. Let me actually make this a little bit bigger. I'm sorry. So take your observation 1, that's what we had pulled out there, minus mu hat 0, transpose it, multiply by the inverse of that sigma hat, multiply by obs 1 minus mu hat 0 again. Do the same thing for group 1, but now you just use mu dot hat 1, and this is what we get. Okay, so the first, and the labeling of the columns isn't very good. The first column corresponds to group, or good equals 0. Second column is group equal 1. So what should we predict for observation 1? Which group? Group 1, because it's a small Mihalowitz distance. I can put this all into these posterior probabilities. So remember how we saw e raised to the negative 1/2 times that distance divided by then e to the negative 1/2 times the distance for group 0, plus the same for group 1. And I do that. And here are my values. These are exactly the same as what we had from what R produced to us. Okay, so it's a lot of work. But I mean, this is the level of detail that I would like you to understand this stuff. You know, I could ask you on a question. I could ask you a question on the test. Calculate the Mihalowitz distance for a particular observation on a data set, and then find the posterior probabilities. Okay. Now, there's some other work here that you can look at on your own, but you're not responsible for. If you remember, there's also what's called the linear discriminant rule. Well, I show the details of how that can actually be calculated here. If you remember, unfortunately, the LDA function R doesn't actually compute it exactly the way that most people would. And so I don't have something I can directly compare to. But this is how all the calculations would be done, but you're not responsible for that. Okay. So essentially what we've done is an example of what resubstitution gives you in terms of the classification or the prediction of a particular observation. Well, we talked about last time how that's not necessarily always the best way. It's not going to give you, let's say, in the end, if you look at all your observations this way and look at how often you are correct, it's not going to give you necessarily the best estimate for the accuracy of your method. And so another way that we can do to get an estimate of our accuracy is to use cross-validation. To review, what cross-validation represents is I'm going to take, let's say, observation 1 out of the data set, do all the calculations that we just essentially did now on the remaining observations. Let's say calculate the mean vectors, calculate the covariance matrices on the remaining observations, put that into that expression that we just saw from Mihalowitz distance, the posterior probabilities, where now our X is observation 1. Then I determine, okay, should this be in, let's say, group 1 or group 2? Then I put observation 1 back into the data set. I take observation number 2 out and repeat those same observations where I try to predict the classification for group 2, and I keep on going. R has automated methods to help you do this. The syntax of the LDA function exactly the same, except for now we say CV equal true. CV for cross-validation. I'm going to do that here where I put the results into an object called DA2. Now, once again, the stuff that's in DA2, if I were just to type DA2 at the command prompt, it's actually even looks worse than what we had for DA1. I'm disappointed at this aspect of R that they could have done a lot better. And so I would never actually even print off DA2. I don't have access to saying, let's say, summary parentheses DA2 in parentheses. That doesn't work either. And so instead, if we look inside of DA2, the main thing that will be of interest to us is the posterior component of the returned list. And so for observation 1, if we look at what we get for that posterior component, we get these posterior probabilities. And again, we would classify observation 1 into the success population or success grouping. Notice this value here, 0.8896. Let's compare that to what we had before. Where is it? Oh, we'll just go all the way up. 0.88997. And in fact, you could look at some of these other posterior probabilities. And I know it's a lot to remember from just looking at it just for a little bit. I will tell you that these posterior probabilities are quite similar. Why do you think that they're so similar? It's just one observation. We have a lot of observations. I think that additional part is helpful to know. So we have about, let me actually look. I think it's 1425. So I say n row place kick. That gives me the number of rows in that data frame. And yeah, 1,425. So, these calculations are being done on very, very similar versions of the data set. That's why we had such similar results. And you should expect this in other applications too. And what this also, though, shows you too is that maybe resubstitution is not necessarily that bad as long as you have a large sample size. Okay? And cross-validation isn't perfect. We talked about other ways that are better than cross-validation. But cross-validation is kind of a standard that people use. And it still will probably, let's say, overestimate the accuracy a little bit. But not too much, especially when you have these larger sample sizes. So let's talk about some more about, well, how good overall is this discriminant analysis method here? And to help summarize overall, is this method getting the predictions right? I've written a function simply called summarize.class for summarize the classification, summarize the predictions. Let's first apply the function, then we'll talk a little bit about how one can understand what's inside the function itself. So if I apply this function, I say summarize.class. The first argument is, well, what were the original groupings of the data? And so I just simply extract out good from the place kick data frame. And then the second argument is classify. Could call it predict. And that just says, okay, what were the corresponding classifications? And so using the results from cross-validation that are stored in DA2, if I say $class, that gives me the automatic groupings or predictions. So I put that in there for classify. And then I get two tables produced. And so what this 124 represents here is that 124 times, the original grouping was 0, meaning a failure. And discriminant analysis also got it right. It predicted 0. But 39 times, the original classification was a failure. But discriminant analysis says, hey, let's predict that as a success. So there are 39 errors there. Let's look at proportions. What's the proportion of times that it got it right? And so that's what the second table gives us here. So this 0.7607 is 124 over 124 plus 39. So there were a total of 163 failures in the data set. 124 times discriminant analysis got it right. In other words, 76% of the time. 24% of the time, it got it wrong. Okay? Well, let's look at the the success place kicks. 274 times discriminant analysis got the prediction wrong. It classified it as a failure. 988 times it classified it as a success. It got it right. So 78% of the time for these types of place kicks that were actually successes, discriminant analysis got it right. What's maybe the overall correct rate? That's what this 0.7804 represents. That's 124 plus 988 over the total sample size of 1425. Yeah. Okay. So 78% of the time it got it right. Definitely not perfect. But that's how well this method did. Okay, so if you notice here, we have these dollar signs that are leading those groupings of items. What this means is that R is returning a list to you. So let me actually run some of this. So let's say that I saved the results into an object called temp, for the lack of a better name. And if I say names temp, if I say temp $prop, that's how I can extract that information. Okay. Let's look at the let's do a little bit of an exercise about how we can actually, let's say you're presented this function. You want to know more about what's happening essentially line by line. How would you actually do this? This is a useful technique to understand whenever you're using R. And so we can see in this function here, I'm passing in two, let's say, bits of information into it. And so what I could do is go from when I ran that function. How about I just say original gets the results from place kick good, classify gets the results from DA2 class. Okay. So for example, oops. There's all those zeros and ones. So now I wonder, okay, let's say I never seen the table function before. So how about we just run this code? And now I can say, okay, well, let's see what it gives me. Okay, so now we can see that first table that was actually produced. Then I run this code. I see what it gives me. So notice what that does. It actually sums up each of the rows in that previous table. And I could keep on going throughout this function here, execute it line by line, so that I can see what is going on. That's how you learn how R, if you're presented with unfamiliar code, some new code, this is how you can teach yourself about what's going on inside of it with this simple technique. Any questions about that? Okay. Well, how about we actually apply this function now and do resubstitution. So again, original, place kick $, good. Previously from last time, we actually put those predictions, those groupings into something called pred.resub. And if we extract out the class, we get those corresponding classifications. And so here we can see overall about 78% were correct. Or I'm sorry, let me just double check something. Okay, I apologize. I jumped ahead there. Let me make sure I didn't skip something in my notes. Just give me one moment. Okay, so this is where we actually went in the notes from last time, and we actually use the predict function to find the classifications using resubstitution. Let me actually just run this. I was just thrown off by the values were exactly the same. I think I might have made a copy paste there. So simply this number here that's in the notes should be actually 0.7811. A very small thing. Any questions about that? Excuse me? Say that again.
There's a little change in the problem matrix too. Is that 20?
Okay. Yeah, a very small change. I have a feeling I was just moving some stuff around in my notes when I put it together, and I made a copy paste there. So please realize this. I mean, it's very small in the end, but of course we want to get it right. Okay. Well, if you remember, I also have a validation data set. And I guess, again, what a validation data set represents is it's often referred to as a holdout data set. So before the analysis actually began, what one can do is split your main data set itself into two parts. One part to actually, let's say, compute the mu hats, compute sigma hat. And you could use cross-validation and resubstitution to measure how well it does. And then you can apply this discriminant analysis method now to some data that wasn't involved at all in the process of determining what mu hat and sigma hat was. And this should give you a little bit more of an unbiased estimate of how well your method does. And so if you remember, I do have a validation data set, it's invalid. And so what I can do is take the results from DA1, our original implementation of LDA. You cannot use the results from DA2, unfortunately. It had to be DA1 when we originally were kind of doing the resubstitution stuff. Just realize that, because otherwise that could throw you off when you're wondering, why isn't this working? And so if I say predict using information from DA1, my new data, being the validation data set, I can put all that results into something called pred.valid. Again, I can then look at the corresponding posterior probabilities, and I can also use my summary.class function, and this is what I get overall. Notice my overall correct classification rate is 0.76, which is a little bit lower than that 0.78 that we had before. This is essentially to be expected, because now this is totally independent of how the method was actually developed to begin with. So I'm not alarmed by that. I expect to see something like this happen. Fortunately, it's not too far off. Okay, so that's the basic explanation of working with discriminant analysis. Let's look at now how we can generalize some of these techniques. We're going to look at 3 different generalizations. One, well, in some situations, making a particular kind of prediction error is more, let's say, costly than the other kind of error that you can make if you just have, let's say, 2 groups. How can we take that into account? Also, how can we take into account that if my population isn't, let's say, 50% group 1, 50% group 2, how can we take into account that maybe I expect, let's say, 75% to be group 1, 25% to be group 2. And then lastly, what happens if we can't assume equal covariance matrices? How can we take that into account? And so that's what the next few pages of the notes talk about. I don't know, some of the details are maybe more than what I needed to get into. Maybe I should just give you the end result. And the end result is simply going to be, we're going to adjust that expression that we saw from a Mahalanobis distance. That's it. So maybe have that in the back of your mind. That's where we're getting to. I'm just going to give you some of the details about why we make that adjustment. And so to begin with here, about how one type of classification or prediction error might be more important than another, let's look at this in context of, we'll do HIV testing, but this works for any kind of infectious disease testing. And, we have this table here kind of summarizing what could happen if you got an HIV test. Where on the rows we have what is true. Either you do have HIV or you don't. On the columns, then we have what a test could give you. So, for example, if you're actually HIV, if you actually do not have HIV and you tested negative, that's a correct classification. Similarly, if you do have HIV and the test gave you a positive result, that's a correct. But we can also have incorrect ones as well. So overall, you could have HIV, but test says negative, and you could not have HIV, but the test says positive. So there's two possible errors that could happen. Generally speaking, which error do you think is more costly, more severe?
Not having HIV.
I would say the other one. But thank you for volunteering. Obviously, both are not good. But think of it this way. If you truly have HIV, the test is negative, then you might be thinking, okay, I feel good about myself. And, unfortunately, you could actually spread the virus to other people. And so typically when these kinds of infectious disease diagnostic tests are developed, one is very, very, very concerned about that error and really wants to minimize that. The other error is obviously of concern too, but most likely what would actually happen in practice is that at some point you're going to be retested again. And if that test comes back negative, then they might think, oh, well, maybe the first test was incorrect. It is actually my statistical research has many, many applications in infectious disease testing. So I deal with these kinds of things all the time. And before I actually got into this area, I didn't realize the probability of error is really, really significant, let's say. Let's see. So I end up working with a lot of sexually transmitted diseases like chlamydia, gonorrhea, and the test there for, I think, gonorrhea is like you will see 92% accurate, or in terms of this right here, about 92%. Chlamydia might be like 97%, 98%. And so there is a significant chance that the test could get it wrong. Well, why? And this is now going beyond what we need to talk about in this class, but I think this is important. Well, why does that happen? There's what's called a window period from infection to detection. The virus, or in terms of chlamydia and gonorrhea, it's a bacteria. It takes a while for your body to have enough in that in order to actually come back with a test that's being positive. Obviously a great case that we've just recently seen in the last couple of years was COVID. If you think maybe you're infected one day, you want to wait until at least 3-4 days after before you actually get a COVID test because of that. And so there's that window period. With like HIV tests, I typically seen window periods of like up to 21 days, where It depends upon the actual test itself. But if you're using what's called an RT-PCR test, which basically is trying to detect the genetic material, the RNA of the virus, 14 to 21 days is the window period. Okay, so, is there a way that we can take into account that one type of error might be more important than another? And the answer is yes. So what we could do is define what's called a cost function, where this notation here, C parentheses I given J, means, like if I said this, suppose I had two populations, given that I'm from population 2, or that I actually have grouping 2, what's then the cost of misclassifying it into group 1? And similarly, I could have this, given grouping 1, what's the cost of classifying it into group 2? And these are subjective in terms of what you assign as a cost. So maybe I could say, this is going to be 10, this is going to be 20. And so what that means is that this kind of error is more costly, it's twice as much as the other kind of error. It is subjective, though. Of course, if I had C of, let's say, 1 given 1, that's a correct classification. So there should be no costs involved with that. Then I can also define, what's the probability of making one of these errors? So that's what probability I given J represents. So the probability, let's say, probability of misclassifying an observation as group 1, given it was actually group 2. I could define those probabilities. And I could also define a set of what are called prior probabilities. Think of that name prior, and where we've seen that earlier in this set of notes, where I can say, okay, now maybe P1 is, let's say, 0.75, P2 is 0.25, which represents 75% of my observations are coming from population or grouping 1, 25 from grouping 2. With this kind of a setup here, one can look at what's known as a Bayes risk. This is a term that you will see in some statistics classes. If you're familiar with Bayesian methods, we're not doing a full-blown Bayesian method here, so don't get mixed up with that. But what we're trying to do is look at, on average, what is my cost of a misclassification through applying some kind of decision rule that this is group 1 or this observation goes to group 2. What's the average cost? And that's what Bayes risk represents. And so you can think of it this way. Here's my cost, the probability that is going to happen, this kind of an error. This cost, the probability that kind of error is going to happen. And then we weight it by, what's the probability that I originally had an observation from group 1. Notice this 1 here matches up there, matches up there. And we can see a similar thing then on the other side. And so this is an average cost of misclassification. And you might be thinking, okay, let's say I have one way, and it doesn't even have to be discriminant analysis. I have this method to classify the observations or predict the observations. I have this method here. Which method is best? Well, you want the method that has the smallest average cost of misclassification. And what does that is what's called a Bayes rule. And a Bayes rule, in the end, it might look a little bit complicated there, but it's actually fairly simple. We see two components that we've seen before: the cost and these prior probabilities. Now, what's inside of here, though, is just simply like a probability density function. That's all. So, for us, it's going to be a multivariate normal. So this 2 here represents, okay, population 2, we're grouping 2, This theta 2 is just a fancy way of saying, hey, we have some parameters that we need to estimate, and we're just trying to be very general with a probability density function. If it was a multivariate normal, this theta 2 would basically consist of all your means and all your variances and covariances. That's all. And so what we would do is calculate this quantity on the left, calculate the quantity on the right. If it's greater, we classify it into group 1, otherwise group 2. This is a very general way of looking at stuff. And in the end, yeah.
I think I don't understand the concept of cost growth because in the numerical method, the cost is like how many flops do we have to calculate some things. But I can understand the concept here.
It is a subjective thing to choose a cost, and this is something like, let's say, the person who's developing a discriminant rule in this case would have to choose. The example that I gave was, well, maybe we should make this 20, maybe we should make this 10. And all I'm saying is the cost that's on that right-hand side is twice as large as the costs on the left-hand side. Somebody else might choose, okay, maybe this should be 100, and that on the left side remains 10.
Oh, so we just give the number.
Yeah. And so you can see that there is some, it's subjective, and it could lead to different answers. We'll talk more about costs as we go along. Now, if I were to replace these probability density functions with multivariate normals and assume that the covariance matrices were the same, also if I assume the costs were the same and the prior probabilities were the same, notice what would happen. Things will cancel out, and I'm left with simply just comparing two different multivariate normal densities, which is exactly the same as the likelihood rule. Exactly the same. So this ties it back to what we did before. In the end, though, if we don't make that assumption of all the equalities, this is what we end up getting. This is the most important thing to get out of this. We simply adjust the Mahalanobis distance by stuff that you see on the right side there, the natural log of the prior probability times the cost. Don't worry about a derivation or anything, but that's what it ends up, what happens. And we predict the corresponding group by looking at the different distances. The smallest distance then corresponds to where you're going to classify that observation into in terms of the corresponding group. We can also find a posterior probability using the same methods as before. We just use these adjusted different D's. So how can we implement this in R? The prior probability part is actually really simple. If you remember, in the LDA function, we had an argument called prior. This is where you could specify the different prior probabilities. Before, we just simply made the assumption of equal, just because it was easy to do and help demonstrate some of the concepts. Now, what's typically done in actual application is that, well, you don't know what these prior probabilities are. So what is done is you choose the priors to be what's called proportional to what was actually observed in your sample. So if I observe 89% successes, 11% failures, as I do in my place kicking data set, then I'm going to assume my prior probabilities are 0.11 for the first group, 0.89 for the second group. That's typically what will be done in practice. Rarely do you have a better sense than that of what the prior probability should be. And R, by default, will make that assumption. So if I don't specify the prior argument at all in the LDA function, it assumes the priors are proportional to what the observed proportions were for your groups. Okay? Now, there's one little thing that you have to understand with this to fully appreciate what this prior is doing. You know, let's say that I did want to actually specify my priors to be proportional and actually put the numbers in there for the place-kicking data set. You know, should I do something like this? Or should I do something like this? So it corresponds to, you know, what does R recognize as the ordering for your grouping variable? In this case, we had good, which had values of 0 and 1. And as you might expect in this particular case, the 0 corresponds to the first value, the 1 corresponds to the second value. Okay. Let's say instead, though, instead of good equals 0, good equals 0 or 1, suppose I have this instead. It could either be called actually failure, or it could be called success. What is R going to recognize as the first level for a prior probability of 0.11? Failure. The reason, R will put this into alphabetical order. What happens if for some reason you had something like this? You had, you know, two groupings. One grouping was A, and the other grouping was A as well. It will put this one first. And so the reason, and also let's say if I had two groupings, one was A and one was simply the number 1. R puts the numbering first. So the whole reason why I go through this, and this is important that you'll see in other places too, is that you have to understand how R recognizes the ordering of stuff. It always puts numbers first, and in terms of letters, lowercase comes before uppercase. My function called factors.r, I'm sorry, not my function, my program factors.r examines a few examples to help illustrate that. Okay, so this highlighted part there corresponds to what I talked about before about these prior probabilities. Now, what about costs? Now, I think we all agree that costs can be important. The problem is it's subjective. I think for that reason, rarely, at least in discriminant analysis, will you see anybody take into account costs. I've rarely ever seen that. I think part of the reason is because some of the other methods that we'll be talking about, it's a little bit easier to take into account costs. But since people rarely will ever put costs into this analysis for discriminant analysis, there's not a good way in like the LDA function to do it. If you find yourself in a situation where you would like to actually do it, here's how you can. You just simply, I've seen books refer to this as you trick the software. You simply adjust your prior probabilities to be those. Well, why? Well, take a look at this expression that we saw before. Notice how these are right next to each other like that? And so essentially what we're going to do is we're tricking the software by saying, okay, the software assumes the costs are all equal, so the costs fall out. But if I change this prior probability to something else, then I can sort of get the costs in there. And so that's what the trick is. In this class, we won't ever deal with using different costs, but still I think it's good to at least introduce that it is possible, and so that's why I like to still talk about that. So we've talked about two extensions to what we've talked about before. Here's the third one. What happens if you have unequal covariance matrices? In the end, you can write out your Bayes rule. Remember how you have those multivariate normals that you would have in there? And the main thing that we need to get out of this is that the distance changes some more. And now you can see you have a different covariance matrix in there. Now, of course, in actual application, we don't know what the sigmas are. We don't know what the mu's are. So you could say di star star hat is this. Okay? Now, whenever one assumes unequal covariance matrices, people now will refer to this as a slightly different name in terms of what you're doing for the discriminant analysis. So we've talked about linear discriminant analysis before. The linear comes from if you were to actually write out that thing called the linear discriminant function. We see that's it's a linear function of your x's. Here, because of now this extra part, if I were to write out that discriminant function, now it becomes a quadratic function of your x's. I don't actually show it here. You can, if you really are interested in seeing it, it is in multivariate analysis textbooks. But it is a quadratic function of x now. And so because of that, people will refer to this as quadratic discriminant analysis when you use this particular distance. So we have now linear discriminant analysis, which what we've been applying previously always, and now quadratic discriminant analysis. So you might be wondering, well, maybe I should just always use quadratic discriminant analysis all the time because there's less assumptions. You could do that. I think it's best, though, typically to try both. Most real-life applications, it's not going to cost you much to just simply run both for an analysis and see which one gives you the better results. In the past, people would say, okay, you could actually perform a formal hypothesis test for your covariance matrices. If you reject HO, then you should use quadratic discriminant analysis. If you don't reject HO, then okay, maybe linear discriminant analysis is okay. I don't teach that approach anymore because I think it's just it's simple to do this. And after all, what are we interested in is how good these methods are, how accurate they are. This information here does not give you that, does not address that. If you reject or don't reject that hypothesis. So just apply them both. Okay. So let's actually look at an application of doing this. So one way to find that indeed the proportion of successes in the observed data for place kick is about 89%. One way to do that is to take the mean of place kick $sign good. Notice I'm talking about proportion, though. What proportion are successes? But I just used the function mean. Why can I use the function mean here? Well, let's look at a situation such as this. Suppose in my sample I just have 3 observations. 1s denote successes, 0s denote failures. I have those 3 observations. What's the proportion of successes? 2 out of 3. Suppose instead I took the average of all those, of the 1s and the 0 there. What do I get? 2 divided by 3. So that's why I can simply take the mean of 1s and 0s to get the proportion. Some people may not have seen that before, but I just wanted to bring that up. Okay. So let's apply linear discriminant analysis first with Pryor's proportional Priors prop. And so to do that now, notice in my LDA function, I do not put priors at all. I put the results in DA3. Notice also I'm saying first or CV equal false. No cross-validation. The reason why I need this, I'll actually put this here as emphasis. Need for validation data when I want to predict those classifications. That's the only reason why I'm doing this. Now, if I do want to apply cross-validation, I say CV equal true, I put the results into something called DA4. We can take a look at posterior probabilities if you wanted to. Remember that first observation that we've had before? Now this is with DA4, so when I'm using cross-validation. Remember, I think the probability that it was in the success or the one grouping was like 0.89. Now it's 0.98. The reason why that went up is because this is taking into account the fact that in my actual sample itself, I have many more good equal ones than good equal zeros, where before I was assuming it was a 50-50 split. And so because of that, it pushes that probability up. I can use my summarize.class function to take a look at then the corresponding results. This, first of all, is with cross-validation. Notice this number, how much higher that was than what it was before. What was it before? Sorry, I don't remember off the top of my head. 0.7, that's actually wrong. About 0.78 before. Now it's 0.93, I believe. Yeah, 0.939. So I'm doing a much better job of predicting those successes. But it comes at a cost. Now I'm not predicting the failures as well as I did before. Sorry, I don't remember. I'm not going to flip back again. But I do know that this is lower. But what's the overall effect, though? Before I was at 0.78 for the correct overall accuracy. Now I'm at 0.87. So by taking into account these priors proportional, this method's doing better overall. Now you have to be careful here. Overall I'm doing better. And the reason being is because since there's just so many ones, and I'm predicting them better, that's why that number is going up, even though this number is going down. In some other application, though, if I was very concerned about, let's say, these zeros, so maybe it's not place kicking, then that might concern me that went down. And maybe even though my overall correct percentage is better, I might not want to use this method because of this number going down. What about for my validation data set? So this is when I use my results from DA3. Look at how this number has gone up, this number has gone down, this number has gone up. Notice again the validation number, or overall correct accuracy, is lower than from cross-validation. Again, we would expect that typically to occur. Okay, so some comments here. I think I've talked about this. Yeah. Well, what about now quadratic discriminant analysis? That means, again, I can get away from the assumption of equal covariance matrices. There's a function for that. It's called QDA, quadratic discriminant analysis. The syntax is the same as what we've seen before. I put the results into an object called DA5. Notice first time through, I'm not going to use cross-validation. And the output looks very similar to what we had before for LDA when we did not use cross-validation. We get summaries of the group means. Notice what we see too is estimates of those prior probabilities. Now to use cross-validation, all I do is assume, or I put CV equal true. I put the results into DA6. And this is what I get. Take a look at for cross-validation, take a look at that first posterior probability. Now it goes down. Now it's 0.78. That's interesting. How about we summarize in the results using summarize.class? Now the correct classification rate for the successes is now about 0.91. So it's a little bit lower than what we had when we did not make the assumption of when we did make the assumption of equal covariance matrices. Notice this value for the failures goes up to about 0.45. My overall correct classification rate is about 0.8568, which is a little bit lower. Yeah, a little bit lower. I can also now work with the validation data set. And I get 0.84 as my overall correct proportion. Okay, so obviously I've went through this output a little bit faster than normal. It's because it's the application of the same functions that we've seen before. Again, with anything that we do in this class, one of the first places that you should start at when you're studying the material is make sure you can verify that the corresponding code, you can run it and you understand what happens step by step. But here's a nice little table. So whenever you use any kind of method where you're trying to predict the groupings, not just discriminant analysis, but also the other methods that we'll be talking about for the rest of the semester, you should always go to a table like this, where you actually write out the results in a form like this. Okay? And so what this does, it allows you to see, so for example, I use linear discriminant analysis, equal covariance matrix, priors equal, cross-validation, validation data set. Two different versions, and we can see the correct proportion for successes, correct proportion of the failures, correct overall. So if my number one goal was the overall part, I look at where do I have the largest values. Linear, equal, proportional. And if my overall goal is that overall, this is the method that I would choose to actually apply. If I'm writing a paper, I would do this. In like a web appendix, like a web appendix for a paper, I would say, I also tried such and such. And my overall proportion of correct classifications was smaller. This is how I would approach it. Okay. Let's actually, because we're running out of time, let's talk about the next project. So this will be the last project of the semester. And again, it gives you an opportunity to show me that you understand the material. It's divided up into 3 different parts: discriminant analysis, and then the next section of the notes will be called nearest neighbor, and the next section of notes after that's called logistic regression. Let's focus on discriminant analysis here. Now you need to have a data set that is appropriate for discriminant analysis. Some of you, based upon project 1 and 2, you could probably use your data. Others of you may not. The key is you need to have some kind of grouping variable that you want to predict. If you need help in making a decision of can I somehow use my data to fit this, let me know, and I'll give you my thoughts on it. But I do think some of you probably will need to go get a new data set for this particular project. The project number 1, I gave you some sources for where to find data, but there's also obviously many other places too that you can look at. If you choose a different data set, though, you do need to clear it with me. So, if you remember on project number 1, there was some like intro stuff where, you say, okay, here's my data. This is where I found it. Here's like the goals of what I'm interested in. Just fill that out and send it to me along with the data, and I will take a look at it. So, for this particular project, number 1 here, perform a linear discriminant analysis using the proportional priors and cross-validation. Provide the classification table with the help of summarize.class. Discuss how well the classification method performs overall and with respect to the specific groups. Similar to what we just did. Number 2, state the posterior probabilities for the first observation obtained from the results in 1. Remember how we were doing that often. Justify the classification for the observation based upon these probabilities. Now, in this particular case, I'm not actually expecting you to go through the matrix algebra. However, I strongly urge you to go through the process on your own to verify that you can do it, because I could put a problem on the test like that. Number 3 here. This is something we haven't got into yet. But, you can imagine the stuff that we've done with like cluster analysis, where we actually, let's say, found plots of the principal component scores. And we look to see, does the clustering results make sense? Well, you can do the same thing here for discriminant analysis. Get the principal component scores for your independent variables. Then have the plotting point correspond to the classification or the prediction based upon discriminant analysis, or the actual true grouping. And so you could actually have, let's say, 2 different plots, one for the classification, one for the actual grouping, and you can see, where does my method fail? Where is it getting the groupings wrong, the predictions wrong? And that's very informative. And so that's essentially what number 3 is talking about. Number 4 then says, okay, let's perform quadratic discriminant analysis now. Summarize the results. So we will continue talking about then the other parts of the project once we correspond to that material. So we're basically just about out of time. So what's next in our class? Well, of course, I'll have office hours today. Thursday, we will finish up discriminant analysis and we will start the nearest neighbor analysis. Looking further ahead, this project number 3 will actually be due 2 weeks from today. So note that don't waste time if you need to go find a new data set. Try to get that done, I would say, this week. Test number 3 is Thursday, November 30th. Any last questions? Okay, that's all for today.